on your syllabus it says experiment 12 and 13. The doing, so the pre-lab part, is experiment 12. You could show maybe a diagram or two from experiment 13, which is the TLC part, and we'll look at those, some of those here in a little bit. But mainly, it's experiment 12 with maybe a little equipment from experiment 13. You'll have a quiz this week. Next week is Thanksgiving week, okay? So we won't have lab on Thursday. Therefore, we will have, I'm going to jump down to the open labs schedule and then go back there. We will have labs open on Tuesday for open labs, okay? So next week, Monday, regular open lab schedule. Tuesday, we'll have labs open from 9 a.m. to 5 p.m. And then Wednesday, right before you leave for Thanksgiving, we'll have them open 9:30 to 12 p.m. Okay, 9:30 a.m. to 12 p.m. So, also with no scheduled lab next week, there's no lab lecture on Monday. Okay. Yes.
So Tuesday lab sections are not meeting either.
Yeah. If Thursday's not meeting, Tuesday's not meeting. So it's kind of the flip-flop of fall break. Okay. So no formal labs meeting next week. Okay. But here are your open lab options. No pre-lab lecture. One thing that you do need to work on, though, is your experiment 8 and 11 report is due next week. So you'll be getting your GC data from your lab prof this week if you haven't already got it for this report. Remember, it's a combined report, so pre-lab, experimental are separate by the combined conclusion, and this one's 75 points, just like experiment 7. Okay? So once you get that GC data, hang on to it too. Okay, you don't want to lose your GC data. So a couple things about that GC data. Make sure, look at the peak list and the chromatogram, okay, for each sample. So you have an idea of what's going on, okay? So make sure you're not just looking at the peak list, because in theory that has all the numbers you need to put your table together, but also look at the chromatogram so you can see where peaks are, see where big peaks are relative to small peaks, things like that. Maybe peaks that were so small they weren't marked, but they're there. So look at both the peak list and the chromatogram. Okay. Then use the GC standards that you were given by your lab prof. So you should get a table from them of GC standard retention times. If you're in a Tuesday lab, make sure you have a Tuesday list. If you're in a Thursday lab, make sure you have a Thursday list. They were slightly different between the two, okay? So if you're looking at someone else's list, make sure you're in the same day of lab if you're using someone else's standard retention time list. Otherwise, you need it for your specific day, because the standards vary just a little bit, okay? And then when you are looking at your peaks, if you can't identify a peak, it's going to be an unknown peak. But be really careful calling things unknowns, okay? You have to use that list of standard retention times to figure out trends, especially within the alkenes. Not all the alkenes that were possible are listed on that list, okay? So you have to use the trends to then make identifications. There's some identifications you're going to have to make that are not on that list of standard retention times, okay? So if it's not on that list of standard retention times, make sure it truly is unknown and not just you can figure out what it is based on the trend that you've got, okay? So if you've got a peak that's sitting in amongst all the other alkenes, it is probably not an unknown. It is probably an alkene you need to identify, all right? Also remember, ketones come slightly before the corresponding alcohol. The ketones are not on that list. but you should be able to identify what is a probable ketone if something comes right before your alcohol, especially if you see it in your experiment 8 and your experiment 11 GC, because there's nothing we did that would have gotten rid of it. All right? So just be really careful labeling things unknowns. Make sure you're absolutely certain that they truly are. All right? Okay. Enough about that. We'll start with experiment 12. Okay, so Sanford left a note that this is a new reaction. Is this a new reaction for every Diels-Alder? Awesome. I love it when they set me up like that. See, ideally they covered this before you came to lab lecture, but they didn't. And they didn't tell me either. All right, so you're going to get a preview of the Diels-Alder reaction, which you are going to see in lecture, I'm sure, as well, okay? But this guy's a pretty cool reaction because there's so many things going on with it, and it happens in one step. So, so here's kind of like a little very basic demo of the Diels-Alder reaction. You need a diene and you need an alkene to be reacting, okay? And you need a diene usually and what we call the other alkene we call a dienephile, all right? And in one step, the two of them come together, they react, there's no intermediate, anything like that, just comes together in one step. You have a cyclic transition state, and you get a ring, and you've made 2 carbon-carbon bonds. So as far as organic reactions go, this is like a high-dollar reaction because you get a lot out of this reaction if it's something that could work for your chemistry. Okay. So this is a really commonly used reaction outside of the McMurray textbook. So like McMurray presents like all sorts of cool reactions, but actually reactions that really get used. This, just like the Grignard reaction, gets used all the time because it is so useful. Okay. So couple things that you need to know about it. There's a lot of adjectives that are used to describe it. First of all, it's a concerted mechanism. So concerted means it happens all in one step. We don't have an intermediate. It just has a cyclic transition state. That I'm not going to go into a whole lot. You guys will see that in lecture, okay? Along with this adjective, a similar adjective is it's a Peri cyclic mechanism. So single step. And we look at this reaction as a redistribution of electrons. So we'll look at that here in a minute. It's also known as a 4+2 cycloaddition. So that comes from the diene, the 4 carbons of the diene, and the 2 carbons of the dienephile. And what you need for this is head-on overlap of p orbitals of the diene and dienephile. And so this is important because this sets up how the reaction is going to actually occur. You have to have this overlap for the reaction to occur. So that also sets up what products you're going to get out of it. A big thing, part of the concerted mechanism too, in concerted, our stereochemistry is concerted. So we don't change stereochemistry. So the stereochemistry of the starting materials is the same when you start as what you get out of it too. Okay. So in that single step, you also keep your stereochemistry. So part of that bottom statement is this comparison of an endo product and an exo product. So what you need is you've got your dienophile, or sorry, your diene has 4 carbons, your dienophile has 2 carbons. You're looking at the overlap of the p orbitals to come together and be able to react. In order for that to happen, you've got to have good overlap of the 2 pieces. So what you end up getting is the endo product, this guy here, okay? You don't get the exo product because you won't get enough overlap of everything that needs to overlap to react, all right? So with Diels-Alder, you always get the endo product, not the exo product. So that's another important piece to it because you can predict easily what product you're going to get out of it, okay? So endo product, you'll have good overlap of your diene and your dienophile. Exo product, you wouldn't have as good overlap, okay? And so not everything would come together in order to have a reaction, all right? So important with this reaction is you want to be making sure you're drawing the right stereochemistry when you're drawing the products, okay? Now we're going to look at the two pieces. So we've got our dienophile and our diene. So this dienophile, it's called a dienophile because it wants to react with a diene, okay? And so in order to make it react with something that has some electron density, what you want to do to set up to have a really good dienophile is have some electron withdrawing groups on this dienophile, okay? So we could have, we could just have ethylene and try and see if we get a reaction. But you're not going to get a really good reaction with just ethylene, okay? Because there's nothing really driving it to want to react with the diene, all right? So what you want to do is put some electron withdrawing groups on it. So something like this, if we had this guy, which now has an aldehyde on it, we've got an electron withdrawing group on it. This makes it more reactive towards that diene, all right? Or if you made something like this, with an ester on it or a ketone on it, making it more reactive, okay? So not just the ethylene by itself. So key to this being a good reactive species is the electron withdrawing groups. The diene has to take on a certain conformation in order to react with the dienophile. So it is set in the S, it's called the S-cis conformation. That's what you want for your diene to react. Okay? If you have it flip the other way, if you have it looking like the S, so this is S-trans, it won't react. Okay? So it has to be S-cis. So either it's got to have a reason to be in this conformation or be fixed in this conformation so that it will react. Okay? And our diene is set in that conformation, so it's going to be really reactive. Yeah?
Is there a difference between the aldehyde version of the dienophile and the ketone version on how well they react with the diene?
There'll be a little bit, but as long as you get that electron withdrawing group on there, it's going to be a lot better than this option.
Okay.
So yeah, there is, like, in between them, there'll be a little bit of difference. Okay, so let's look at our reaction. Okay, and we have some cool words to say too as well. Okay. So the first piece is cyclopentadiene. Okay, here's our diene. It's a ring. It has to stay in this conformation. So it is in the cis conformation. It's happy that way, and it's not going to change. All right. Our dienophile is N-phenylmalonyamide. Okay, or N-phenylmalonyamide. There's multiple ways to say it. It actually has 2 electron withdrawing groups on it. Okay, you've got this one here and that one there. So even though it's part of a ring, you've got an electron withdrawing group there and an electron withdrawing group there. So it makes it really reactive, right? Your actual reaction this week, you're refluxing for 10 minutes. That's how reactive it is. And even before you actually reflux, your reaction is probably mostly done. Okay? So it's very, very reactive. All right? So in our cyclic redistribution of electrons, okay, we have our electrons from our dienophile. So if you count carbons, first of all, we've got 1, 2, 3, 4 from our cyclopentadiene, 5, 6 from our dienophile. Okay, so our double bond from our dienophile, electrons flow to carbon 1. Then electrons between 1 and 2 flow between 2 and 3. Then electrons between 3 and 4 flow over to carbon 5. Okay? So in the end, here's our 1, 2, 3, 4, 5, 6. So we went from 3 double bonds to 1 double bond. Okay? And again, we always get our Endo product. So this is what the stereochemistry looks like for your product for this week. It's the Endo product. Okay. Now this looks a little bit different than the bare bones example that I gave you because we've got multiple ring systems involved here. Okay. So like this carbon here that we didn't mark is this carbon here at the top of that ring. Okay. So we got a little bit of extra going on here. So you're going to have N-phenylmalonyamide dissolved in ethyl acetate. It's bright, like canary yellow, okay? You're going to dissolve it in dry ethyl acetate, and then you're going to come see us, and we will give you cyclopentadiene, and immediately it will start reacting, all right? And you will immediately, pretty quickly, see that yellow color even dissipate from the reaction. Now, the reason that we will give you the cyclopentadiene is the cyclopentadiene comes from dicyclopentadiene. So dicyclopentadiene, if we do a retro Diels-Alder reaction, so the backwards Diels-Alder reaction, we get cyclopentadiene. If cyclopentadiene wants to react with itself, then it will form dicyclopentadiene. So what we have to do is what's called cracking. We crack the dicyclopentadiene, so we heat it up and we distill it, and we get cyclopentadiene, and then we have to keep that really cold until it's time for you to put your reaction together. So we'll keep it on ice, give it to you, and then it will react immediately with your dienophile. Okay? So there's kind of 2 parts to this. This is the part you're doing, this is the part we have to do before your reaction. Okay? So the retro Diels-Alder reaction is basically just the backwards of this reaction. So if we have the collapsing of the ring that was formed, then we get our 2 cyclopentadienes. Or if we have, just like this reaction, a similar Diels-Alder reaction, then we get the 2 rings coming together to form the dicyclopentadiene. Okay? So just be aware of that reaction as well. So really, for this week, there's not, the reaction itself is not the tricky part of it, okay? So you're going to, couple notes about the procedure. So you're going to have your dienophile dissolved in the ethyl acetate, like I said. Be careful, we're going to talk about TLC here in a little bit. So you need ethyl acetate for your reaction solvent. So remember that it's just ethyl acetate, okay? We're going to talk about TLC in a minute, and you're going to use hexane ethyl acetate for that, okay? Make sure you use just the ethyl acetate to set up your reaction, all right? You'll know you've gone astray if your solid doesn't dissolve because you've got the wrong solvent, okay? So make sure you use the right solvent, and we're using dry ethyl acetate so it's in the reagent head, okay? So after you add the cyclopentadiene, you're going to reflux for 10 minutes. Then you're going to distill the solvent, and the reflux and the distillation is all happening in a water bath because ethyl acetate's boiling point's below water. Okay, it takes a little heat to make it happen, but you're going to reflux, then keep it hot and just convert it right over to a distillation, and then you're going to cool and precipitate the product with hexane, and then you're going to do a recrystallization. And you're using ethanol as your organic solvent for this, so just be careful with the ethyl acetate and ethanol and so forth, reading all the containers correctly, okay? Here you may not have a super nice white product, but it should be pretty close. But when you get to this point, you should have a pretty nice white product. So like I said, as far as the reaction goes, this is a nice, like, textbook organic reaction. Goes quickly, couple minutes, and then you get a nice white product out in the end, okay? So enjoy that moment because it rarely happens, all right? What you will need for the product is, as always, we always want to yield, okay? You're going to want to collect the melting point. You'll want to collect the IR spectrum. So it's a solid, it'll be like polystyrene. You're going to, you have to have the anvil down when you're collecting the product spectrum. And then you're going to be TLCing that last, we're going to talk here in a minute about TLC and what that means, but you're going to want a TLC of that last product, what it looks like, okay? So you want those four things of your product. As far as the IR, on Moodle, there will be cyclopentadiene, N-phenolmalum, and the product IR spectra up on Moodle for you to make comparisons to. Okay, when you get to that. All right. So now what we're going to talk about is what this means as far as TLC. So that is what experiment 13 is. We're talking about, yet again, one more chromatography. So this time, thin layer chromatography. So otherwise known as TLC. And what you have with thin layer chromatography is a plate, okay? And there's some sort of backing on that plate, but then you have silica that is on this plate, all right? The silica is your stationary phase. So it doesn't move because it's stuck on that plate. Your mobile phase is your eluent. or your solvent that you're using. So when you are all set to go with your TLC plate, this is what it's going to look like. So we've got our TLC plate. We'll put some material on it. We'll put it in the developing solvent or the eluent in this developing chamber, cap it, and you don't want to move it because if you move it, you disrupt how that solvent goes up the TLC plate, and you want it to go up evenly. If it doesn't, it makes it hard to figure out what's going on. But that solvent will climb up that plate and be interacting with the silica and what material you have spotted on that plate. Okay? And so there's this equilibrium going on of what you've spotted on that plate going between the solvent that is climbing up the plate and the silica that is basically that plate. So it's going back and forth. Okay? Now silica, is that relatively polar or nonpolar? It's relatively polar, right? And so things that are more polar are going to want to hang out more with the silica versus things that are less polar will probably be hanging out more with the mobile phase. All right? So the other half of that picture is showing spotting the TLC plate. So we'll show you how to make spotters. So kind of the tricky part of this week's lab is learning how to make spotters and learning how to put the TLC plate in the developing chamber so it doesn't get messed up and getting the spots on the TLC plate. So it's like all manipulations, mechanical manipulations, not doing the chemistry part. So when we spot a TLC plate, so you'll have a plate that is cut. We've even been nice enough to put this pencil line on there so you know what line to put your spots on, okay? So if we have a couple spots on our TLC plate, we've put it in the developing chamber, and it's developed. So you want your solvent to come within about 1 centimeter or so of the top of your TLC plate. We've developed this plate, and then we take it out of the chamber, and we're going to look at what's on there, okay? So say we've got two different spots. And the way we visualize what is on here is we use UV light to see what is on there. So there's a dye that is on the plate that helps fluoresce UV active compounds so we can see them, okay? So our N-phenolmalleamide has an aromatic ring on it. That makes it UV active. Therefore, we can see it and we can see the product that it makes, okay? So you won't see Cyclopentadiene on here because it's not as active, but you'll see your starting material and you'll see your product, your other starting material, and you'll see your product on here, all right? So you'll look at this under UV light. We've got a couple spots here. Well, when you've got something that's relatively polar, it wants to hang out with the silica. So that means it didn't really travel with the eluent. So in this example, this spot closer to the origin would be the more polar compound. This spot would be less polar. So did everyone understand that part? It wanted to hang out with the silica more than it wanted to hang out with the eluent in that equilibrium back and forth, okay? Now you can manipulate this, all right, based on the solvent that you use too, because your solvent can be more polar or it can be less polar. So we're going to use a combination of ethyl acetate and hexane. What can you say about hexane's relative polarity? It's not polar. But how about ethyl acetate? More than hexane, right? I mean, it's not the most polar thing you have, but it's more than hexane, okay? So what we could do is make the ratio heavier in ethyl acetate, and then develop the plate. And because it's more polar, things that are more polar are going to hang out a little bit more in it. So it's going to make everything move up, okay? So say this was our starting example. Then we made a more polar eluent. Then we could have something maybe like that, okay? So the more polar eluent made things travel higher on that TLC plate. Okay? Yes?
Will the eluent always be less polar than the silica?
Yes. It's really hard to be more polar than silica, so don't think you're going to flip it, okay? The silica will still be more polar than any eluent you would use. If you get into getting more polar than the silica, you're probably dissolving the silica instead of actually making things travel up the silica. Okay? So like one of those you have to be careful of, well, a couple of them. Don't get your TLC plates wet, because if you get them wet enough, you'll dissolve your silica. It also leaves spots on your TLC plates that are hard to interpret your results. Methanol, you couldn't run a TLC plate in 100% methanol because it would dissolve the silica as it's going up the TLC plate. Okay, so for what you would use for TLC, you're not going to have a solvent system that's more polar than the silica. All right. Okay. So now let's say we decided we want things to be less polar. So now, between here and here, we used a less polar system. What would happen to our spots on the TLC plate? They would be lower down on the plate, right? So we get maybe back to something like that. Okay. So what you use to compare the spots and to make a comparison overall for that TLC plate is what is called the retention factor, or the RF value, okay? Here's our spots again. We've developed our TLC plate. This RF value is the distance the spot travels from the origin and so the origin we're always calling our pencil line, over the distance the solvent travels from the origin. Okay. And so, and usually with a spot you want to take kind of in the middle, as best you can, of the measurement of how far it traveled. So from the middle of that spot down to the origin line, that would be that top distance. Okay, I'm going to label this number 1. I've already used labels, letters here. And our distance the solvent travels is from the origin up to that line that we drew when we pulled it out of this TLC plate, or out of the developing chamber. Okay, so that would be 2. So in this case, whatever the distance is for 1, and typically you measure it in centimeters, over the distance for 2 would be the RF value. Now, you're dividing centimeters by centimeters, so is there units for the RF value? Okay, so RF value is just going to be some number. Is it a bigger than 1 or less than 1? It's some decimal less than 1. Okay. Now, when you were pulling your TLC plate out of the developing chamber, I said let the solvent go up to about a centimeter from the top. What you do when you pull it out is you then mark that solvent line. So you want to kind of do a good job, since you're measuring from that line, carefully mark as best you can what that solvent line actually looked like. And you mark it in pencil. So all the markings you put on the TLC plate, you mark in pencil, because pen has things that will travel up a TLC plate. So if like you spotted down here in ink pen, you would be also developing the compounds of your ink pen up the TLC plate along with what you're trying to look at, okay? So always use pencil. Don't get them wet. Use gloves too, because your hands have aromatic compounds in them that if you touch your hand or touch your fingers on the TLC plate, you're going to leave fingerprints on the TLC plate too, okay? So handle with gloves, use pencil when you're marking them, don't get them wet. The other thing with the pencil is the silica is really fragile, so don't like try and write really hard. You're going to etch out the pieces of your silica, so you kind of have to just lightly write on it too, so you don't destroy the TLC plate, okay? So a couple things that we can use TLC for. We're going to use it to actually look at the progress of a reaction. So what we should see over the course of time. So like I said, you're going to look at your dienophile, and you're going to look at your, for TLC, there's a dienophile standard, and there's a product, the product you should make standard, and then you'll look at your reaction mixture, okay? What you should see over the course of time, hopefully, is you're going to spots that all reflect product, and your starting material has disappeared, okay? So this is what this example is showing you in your lab manual. So we start here at time 0 with our reactant and our reaction mixture, and then our product standard. Our middle lane here, our reaction mixture, we want to head towards this product standard and have less and less of the reactant present. So there may be a point where we have both product and reactant present, but we eventually want to get to the point where we don't really have any reactant present and we only have product and then just the reactant standard, okay? So you're going to use similar to this this week, although it's a little bit difficult to capture it because your reaction is going to go so quickly, okay? So you are going to you want to TLC your reaction, first of all, right after the cyclopentadiene is added to your reaction mixture. So when you go to get your cyclopentadiene from your instructor, not only do you want your reaction mixture ready to go, you also want a TLC plate and spotters ready to go, so as soon as you go back to your hood, you can immediately spot the reaction mixture on the TLC plate. Okay? So be ready to spot it right after, because if you wait any beyond the right after, that reaction's happening, and it's going to happen quickly. Okay? You also should spot at the end of reflux. So that should be the end of the reaction time. So hopefully, at this point, you maybe have a mixture of starting material and product in your reactant lane. Here, you should hopefully only see product at the end, okay? Now, this part is kind of up to your lab prep what they want you to do. But you could potentially then, when you precipitate your product, you could spot the crude product before recrystallization, and then you could spot the product after recrystallization. So see what your lab prof wants you to do. At the very least, you should probably do at least 1, 2, and 4. Okay? And the whole time on your TLC plate, you want to make sure that you are also spotting the reactant standard and the product standard, so that you have things to compare it to. Okay? So these are available in the lab in vials. Just don't be really careful handling them because they're just in little vials, which is all we should need for all week of lab. But if you dump them, then you've dumped all our standards, so then we have to remake the standards. So just be careful handling these guys. Then in the middle here, you could put like 1 spot, or you could put fit a couple spots in there. It'd be kind of tight to probably fit everything in there, so your lab prof will tell you what your TLC plate should look like, okay? But don't forget to put the reactant standard and the product standard on each one, so you have things to compare it to, okay? Now what you don't want to do is you don't want to spot right on the edges of the TLC plate. You want it in a little bit, like about 1/2 centimeter or so. And then you want about 1/2 centimeter in between your spots too. Otherwise, everything will kind of just flow up together on the TLC plate, and it'll be hard to figure out what's going on, okay? Another trick is before you put it in the developing chamber, check and see what it looks like under the UV light, okay? See if you need to add more of the standards, or see if you've got enough spotted on there to be able to see what's going on. Because once it's developed, you can't really go back, especially when you're doing these checkpoints of your reaction. So look at it under the UV light, okay? And then when you're getting your developing chamber together, you don't want so much solvent that you're above this line when you put it in the solvent. You want the solvent to start below that line, okay? So put like 1/2 centimeter or so of solvent in there. Don't put too much solvent in it. Then you want to cap it and let the solvent climb up the filter paper that's in there to get the whole system under equilibrium, and then put your TLC plate in there. So don't dump the solvent in and then dump your TLC plate in, because then you're not going to have the developing of your TLC plate is not going to work out quite right. Okay? All right. So for experiment 12, you guys have a set of worksheets that you're going to, well, a worksheet front and back that you're going to put together. So this part, a lot of it is similar to experiment 6, except for you're reporting your melting point range and yield and percent yield, and get the structure of your product. Then you're going to report what your TLC plates looked like, okay? And so in lane A, you would give a description of what lane A is. Is it the reactant starting material or reactant standard? Is it the product standard? Is it your reaction mixture? What is that description? And then for however many spots you have in lane A, you're going to give all those RF values. So when you're looking at your TLC plates, you need to calculate the RF values for all the spots that you have in each lane and make comparisons, okay? And so what ideally should happen is spots that are the same thing should have the same RF values too. Okay, so like the reactant standard and the reactant in your reaction mixture should have the same RF value. Same with the product standard and the product in your reaction mixture should have the same RF value. Okay? So you're going to do that for each lane, for each plate that you had to make. The plates themselves talk to your lab prof and see what they're going to have you do. You will either draw them vertically. So we always look at TLC plates like this. We don't look at TLC plates like that. Okay? So draw them vertically. Even though it takes up precious room in your notebook, draw them vertically. Okay? Either draw them life-size vertically in your notebook, and then when you're done with it, making the measurements on your TLC plates, you would discard them, and they go in glass waste when you discard them because they're silica. Or your lab prof will have you tape the TLC plates vertically in your lab notebook. Okay, so see what your lab prof wants you to do. Okay. The back side of this worksheet, then, you are going to take the IR spectrum of your compound and then compare it to the literature spectra, are the ones that I'm going to put up on Moodle. And then, so you will be comparing your compound to what did the starting materials look like and what did the product look like. And then you're going to write a conclusion about a page or so that discusses experiment 12. So we'll give you more specifics about this in lab this week. Okay? But to help you out, because what we are making in lab this week is not something you can look up in Aldrich. So it's not like making the polystyrene, or not like even making trimyristin or myristic acid that you can look up values, not like making your alcohols or your alkenes. We're making something that Aldrich doesn't sell. Okay? So I'm going to give you some help out with some valuable information for what you are making this week. Okay? And then while you're copying this down, I was going to also make a note to you, if you have registered for, first of all, if you did not register for 256 A or B last week, let me know if you are intending to register. Like you didn't register, but you're intending to register, because I'm working with the wait list and registration. If you did register, you'll be getting an email from me about information I need from you about lab section or especially for part B. Okay, so just look for the email from me. Okay, and just read the email, and then if it pertains to you, please respond to the email, because we're trying to get information for our sections, finalizing our sections for next semester. Okay. All right, questions you guys have?